Welcome to the deep dive. Today, we're tackling a really big question in Earth science.
A fundamental one, yeah.
How did those huge tectonic plates, the ones making up the planet's surface, first start diving under each other?
That process, initial subduction?
Exactly.
Hmm.
And sounds simple, maybe, but figuring out how and when these massive rock slabs actually bend and sink.
It's incredibly complex. It's genuinely one of the trickiest parts of plate tectonics research.
Right. And to help us unpack this, we're going to dive into a brand new study, just out May 2025. But it's not your typical geology paper, is it?
No, it's not about like discovering a new mineral or mapping a fault. It's actually a study about the studies.
Meta-research.
You could say that, yeah. The authors use some pretty sophisticated software tools to analyze, get this, over 2,100 research papers and reviews published over the last, well, nearly 30 years.
Wow. From 1995 to 2024.
Exactly. All focused specifically on initial subduction.
Okay, so our mission here, basically, is to use this huge analysis of all that research to give you a kind of shortcut.
Yeah, a guide.
We're going to map out the field, right? Who are the key researchers? Where's the cutting-edge stuff happening? What are the big debates?
And, where's it all headed? What are the next big questions?
Exactly. Think of it as the state-of-the-art on how plates start sinking.
Right. This study basically gives us that map of the research itself, shows the paths already explored, and the new frontiers.
Mapping science. That sounds interesting. How exactly did they do that? What was the method?
It's called bibliometric analysis. Imagine it like looking at a giant network of connections.
Okay.
They track things like, publication counts year by year, who's citing whose work, which authors or universities are sort of central hubs in this network of ideas.
Right, like influencers in the science world.
Kind of, yeah. And also which keywords are trending, which topics suddenly pop up or fade away. They started with a massive search, actually, over 6,700 papers. But then they really focused in on 2,107 core articles and reviews that were most central to initial subduction.
So they built this, knowledge web based on the scientific literature. And the main goal was?
The big goal was to get a really clear, systematic picture of how the field has evolved. Track the breakthroughs, identify the most influential people in places, see how different scientific fields are contributing, and, crucially, spot the current hot topics and the emerging trends from the mid-90s right up to now.
Got it. So looking at all those papers over 30 years, did they see, steady, gradual progress, or was it more stop-start?
It was actually pretty distinct phases. The study highlights 4 main periods, almost like growth spurts for the field.
Okay, what were they?
Well, first, 95 to 97, that was the initial stage. Very low output, maybe a dozen papers a year, something like that.
The very beginning.
Yeah, scientists were just laying down the fundamental ideas, theories about, how strong plates are, how the first volcanic arcs form magma, the basics.
Right. Then what?
Then came the stable development stage, roughly 1998 to 2008. Things picked up, a nice steady linear increase, went from about 10 papers a year up to maybe 32.
Okay, so growing consistently.
Exactly. And they started integrating more tools then, using geochemistry, like chemical tracers in rocks and more detailed structural mapping.
Adding more layers to the analysis.
Right. But then things really took off. From 2009 to 2016, they call it the accelerated growth stage.
Ah, the boom time.
Yeah, publication numbers jumped dramatically. Went from 55 a year up to 86. It was almost exponential growth for a bit there.
Wow. What drove that acceleration?
Technology, mainly. 2 big things happened. First, huge advances in high-precision geochronology.
Dating the rocks.
Exactly. Techniques using minerals like zircon got so good they could pinpoint ages down to plus or minus 0.1 million years. That's incredibly precise for geology.
Unbelievable. And the second thing?
Numerical simulation. Computer modeling got powerful enough to actually start realistically simulating these super complex processes of plates bending and sinking.
Ah, so better dating and better models. Makes sense.
Precisely. Better tools just opened up new questions and faster discoveries. And that momentum basically carried right through to the most recent period, 2017 to 2024. They call this the prosperous innovation stage.
It sounds impressive.
Yeah, output consistently topped 100 publications per year. And what's driving it now is really the integration of even more disciplines.
Like what?
Things like seismic imaging using earthquake waves to see deep structures, even machine learning applied to rock chemistry data, and these massive global-scale computer simulations.
Wow. Okay, so the field is clearly firing on all cylinders now. Who are the key people then? The researchers whose work really laid the foundation or drove this recent innovation? The study names some names, right?
It does, yeah. The analysis really highlighted 4 authors who stand out based on citations and how central their work is to this whole network.
Okay, who's first?
R.J. Stern. He's got over 800 citations. His work, starting back in '96, was really foundational for understanding why subducting slabs release water and how that changes the mantle rock above them. Crucial process.
Explaining that fluid release mechanism. Got it. Who's next?
J.A. Pierce also started publishing key stuff in the mid-90s. He pioneered using the chemistry of volcanic rocks as a fingerprint, basically, a way to tell if they formed because of subduction.
Ah, the chemical detective work.
Exactly. And the analysis showed his work has really high centrality. It connects lots of different threads in the research.
A bridge between disciplines, maybe?
Sort of, yeah. Third is S.S. Sun. His paper from 1995 has this incredibly high centrality score, almost 1.0, which is just wow. Meaning it's incredibly relevant across many different parts of the field. He really advanced how we use isotopic tracers, like different versions of elements, to figure out complex processes happening in the mantle wedge right above the sinking plate.
Okay, so Stern, Pierce, Sun pioneers from the 90s. Who's the fourth major figure?
That's Weidelich. He emerged a bit later, around 2009, right when that big growth spurt was starting.
During the acceleration phase.
Right. And his big contribution has been redefining how we classify and understand ophiolites in the context of subduction starting.
Ophiolites, those are bits of ocean crust shoved onto land, right?
Exactly. Finding them in the right context tells you a lot about ancient plate boundaries, including where subduction might have kicked off.
Okay, so we have foundational figures and key contributors during the growth phase. What about where this work is happening? Which countries, which universities are the big hubs?
Looking purely at the number of papers published, researchers in China are leading the pack with almost 700 papers in this data set, followed very closely by the United States with about 640. Then you have Australia, France, Germany, all with over 200 papers.
A global effort, then.
Definitely. England, Japan, Canada are also in the top tier. But what's interesting is Switzerland. They're not top 5 in raw numbers, but their research has the highest centrality score among countries.
Meaning their work is particularly connective or influential.
It suggests Swiss researchers are playing a really key role in integrating different international research efforts, punching above their weight in terms of impact, you could say.
Interesting. And specific institutions.
The Chinese Academy of Geological Sciences stands out. Huge output, over 300 papers, and high centrality, too.
A major powerhouse.
Yeah. Other big ones are China University of Geosciences, the French CNRS, the China Geological Survey, and interestingly, the Institute of Geology and Geophysics in China ranks 5th by number of papers, but has very high centrality, suggesting its work is also highly influential.
It sounds like there's been a significant shift, with Chinese institutions becoming really dominant players in this field. Where does all this research usually get published? Are there specific journals that are the go-to places?
Yeah, the analysis showed that 4 journals really dominate the discourse here.
Okay, which ones?
Earth and Planetary Science Letters, often called EPSL. It's a major outlet, especially for those high-resolution geochemical studies we talked about, linking back to Pierce and Sun's kind of work.
Right, the chemical clues.
Then there's Geology. That one often features studies based on fieldwork, mapping out the tectonic history on the ground.
Okay.
Tectonophysics is another big one, often specializing more in the geodynamic modeling side of things.
The physics of plate movement.
Exactly. And the 4th major player is the Journal of Geophysical Research, Solid Earth, or JGR, Solid Earth. It publishes a lot of the big numerical simulations, trying to model exactly how a slab starts to, buckle and sink.
So modeling nucleation.
Right. And JGR, Solid Earth, despite being 4th in sheer volume among these top 4, actually had an extremely high centrality score.
Meaning it's highly influential across the board.
Yeah, its papers seem to be really widely read and cited across different subdisciplines within initial subduction research. Of course, there are other top journals too, like Nature, GSA Bulletin, Tectonics, but those 4 are really central.
Good to know. So if you want to track the absolute latest, those are the journals to watch. Based on this huge analysis, What are the big questions scientists are really focused on right now?
Yeah.
Where is the research converging?
It seems to boil down to two main areas, really. First is getting much better at identifying and characterizing what they call proto-subduction signatures.
Meaning the very first signs in the rocks.
Exactly. The specific geological evidence left behind that screams, subduction just started here. This involves looking closely at those four arc basalts, the special SSZ-type ophiolites, and certain metamorphic rocks that form under unique conditions.
Finding the geological crime scene, basically.
Yeah, something like that. The second major focus is on the mechanics, the physical modeling. Trying to pin down whether subduction starts spontaneously, the plate just kind of collapses under its own weight, or if it has to be induced, forced by some external push.
Spontaneous versus forced start. Okay. And what are the cutting-edge techniques helping them tackle these big questions?
Well, the study points to continuing improvements in that ultra-high resolution dating. They're pushing towards precision of plus or minus 0.05 million years now.
Wow, that's getting incredibly fine-grained.
It really is. Also, using more complex combinations of isotopes, boron, lithium, strontium, neodymium as tracers to pick apart the chemical processes.
Multi-element fingerprinting.
Yeah. And on the modeling side, things are moving towards these massive 3D numerical simulations using powerful computing platforms like Aspect and Underworld, trying to capture the dynamics much more realistically.
It really sounds like the technology is letting them probe deeper and deeper into this process. Let's just zoom out for a moment. Why is understanding this specific moment, initial subduction, so critical for understanding the Earth system as a whole?
Well, plate tectonics is basically the planet's operating system, right? It controls earthquakes, mountain building, the creation of ocean basins, how materials get recycled between the surface and the deep earth.
The fundamental end.
Exactly, and subduction zones are the absolute core of that engine. That's where oceanic plates sink back into the mantle. That sinking pulls the plates, it releases fluids that trigger volcanoes, it creates environments where many mineral deposits form. But none of that can happen until a subduction zone actually starts. That moment of initiation is when the rigid outer shell, the lithosphere, first fails and begins that massive journey downwards.
Yeah.
It's the weakest link in our understanding of the whole cycle.
It's the ignition switch for the engine.
That's a great way to put it, yeah. And this study shows that the cutting edge isn't just about initiation anymore. It's connected to building amazing 3D and even 4D models of how slabs behave over time.
Okay.
Figuring out how to spot the incredibly faint traces of subduction from billions of years ago, understanding how these cycles link to supercontinents forming and breaking up, like Rodinia or Pangaea,
Right.
and really trying to quantify the forces involved. How much is slab pull? How much is mantle convection pushing things around? Initial subduction is a vital piece in all those bigger puzzles.
Okay, so let's get practical. If you're a geologist out in the field, boots on the ground, what specific clues are you looking for in the rocks that make you say, aha, subduction started right here, around this time?
Right. You need evidence of that critical transition. Signs that an old ocean basin was just starting to get consumed. The study highlights a few really key geological records. One is four-arc basalts, or FABs.
FABs, what's special about them?
They have this distinct chemical signature. They're enriched in elements that dissolve easily in water, like barium,
Okay.
compared to elements that don't, like niobium. That specific ratio tells scientists these rocks formed when fluids squeezed out from that first sinking slab chemically altered the mantle wedge right above it, causing it to melt. You typically find them near the trench zone.
So it's a chemical fingerprint left by those first slab fluid.
Pretty much, yeah. Another really key indicator is a specific type of ophiolite. They call them SSZ type, for suprasubduction zone ophiolites.
Okay, SSZ.
These are basically chunks of oceanic crust and mantle that actually formed in that very early volcanic arc setting right above the new subduction zone. So if you can date when that ophiolite formed, it gives you a really good constraint on when subduction must have started.
Like finding fossils from the birth of the subduction then.
Exactly. And then there's a rock type called bonanite.
Bonanite. Sounds exotic.
It's pretty unusual stuff. It's high in silica, high in magnesium, but really low in titanium. That specific chemistry basically yells subduction initiation.
Why is that?
Because it means the mantle wedge that melted to form it must have already melted before, and it got heavily changed metasomatized by those slab fluids we keep mentioning. It reflects really specific hot, wet melting conditions right at the start.
So the rock's composition is like a detailed diary entry of that specific event.
It really is. And one more key piece of evidence, the metamorphic soul.
Metamorphic soul, like the bottom of its foot.
Sort of. These are slivers of highly metamorphosed rock, think high-pressure granulites, down to green schist facies that you often find plastered onto the base of an ophiolite, usually in a jumbled-up tectonic melange zone.
Okay, what do they tell us?
They show incredibly rapid heating to high temperatures, like 700, 850 degrees C, at significant pressure, 1.5, 2.2 GPa. This points to a really high thermal gradient, really fast burial, and heating right at the interface between the overriding plate and the brand new sinking slab. Intense conditions.
High pressure, high heat, fast changes.
Got it.
And how quickly does this whole initiation sequence happen? Is there a typical time frame?
Yeah, the study notes that based on dating these different rock types using things like Zuron UPB for the magmas and maybe argon dating for the metamorphism, the time gap between the initial magmatism, like the Bonanites, and the formation of the metamorphic soil is usually pretty short, geologically speaking.
How short?
Typically less than 5 million years.
Wow. So it goes from just regular ocean floor to full-on subduction, starting relatively quickly. Okay, so we have the evidence in the rocks. Now back to the how. Spontaneous versus induced. Can you break down those mechanisms again?
Sure. Scientists basically group the proposed mechanisms based on what's thought to be the main driving force. Spontaneous subduction is dominated by vertical forces, mainly gravity acting on density differences.
So the plate essentially starts sinking under its own weight, like a heavy, wet blanket pulling itself down.
That's a decent analogy, yeah. The idea is that older, colder, denser oceanic lithosphere becomes gravitationally unstable. Potential triggers could be something like an existing weakness, like a transform fault collapsing. The older, denser side just starts to founder along that weak zone.
Okay.
The Isobel-Mariana arc system is often cited as a possible example of this transform collapse model. Another idea is the collapse of a passive continental margin.
How would that work?
Maybe thick piles of sediment build up on the edge of a continent, weighing down young, weak oceanic crust nearby until it ruptures and starts to sink. Numerical models suggest this is plausible, especially for young ocean crust, maybe less than 30 million years old.
Interesting. Any other spontaneous triggers?
Yeah, the mantle plume idea. A plume of hot mantle rock rising from deep within the Earth could heat and weaken the lithosphere above it, making it easier for an edge to collapse and initiate subduction. Some people link this to the formation of the Caribbean plate, for instance.
So internal weaknesses, density pulling it down, or maybe a plume weakening it from below. Those are the spontaneous ideas. What about induced subduction?
Induced subduction is dominated by horizontal forces. External stresses essentially pushing a plate into starting to subduct.
Being forced downwards.
Exactly. One classic scenario is during continent collision. The collision might force an existing subduction zone nearby to basically jump location or migrate. There's evidence suggesting this might have happened with the closure of the ancient Bengongku-Nujiang Tethys Ocean in Tibet.
So a collision forces a new subduction zone to start elsewhere.
Right. Or another possibility is polarity reversal. Imagine an island arc or some other crustal block slamming into an existing subduction zone. That collision could be forceful enough to jam up the existing system and actually cause subduction to start in the opposite direction, on the other side of the colliding block.
Flipping the subduction direction.
Mm-hmm.
Okay, so we've got the evidence, the timing constraints, the possible triggers. But this big review study also must have highlighted where the science isn't settled yet, right? The big debates and knowledge gaps.
Oh, absolutely. And this is where things get really fundamental, especially when we try to look back into deep time.
Like what?
Well, one massive question is, when did the modern style of plate tectonics with deep, self-sustaining subduction actually start globally? Was it operating way back in the Precambrian billions of years ago?
We don't know for sure.
It's heavily debated. The study points out a significant problem. When geologists apply the criteria we use to identify Phanerozoic, the last 540 million years, initial subduction to much older rocks like Archean greenstone belts.
Yeah.
The consistency is pretty low, less than 40%.
Yeah,
the features don't always match up well. So, did subduction work differently back then, or are we just not recognizing the signs correctly? It's a huge question.
Wow, that's a major disconnect between the present and the deep past. What else is still fuzzy?
There's also debate about how universal that classic magmatic sequence, the four arc basalts, the bonites, really is. The Isobel-Mariana arc is our go-to modern example.
It's a type locality.
Right. But when scientists examine ancient mountain belts, ancient origins from, say, the Paleozoic era, only about 58% of them seem to show that classic IBM-type sequence clearly.
So more than 40% don't fit the classic model.
Exactly. Does that mean subduction initiated differently in those cases? Or maybe the evidence was just destroyed or altered over hundreds of millions of years? We're not sure.
It really highlights the challenge of applying present-day models to ancient Earth.
It really does. And that ties into the third big debate, the early Earth subduction mechanism. How well does that mantle plume collapse idea really explain how the very first subduction zones got going?
Is the evidence weak?
It's more that the quantitative modeling is still limited. The study noted there aren't many detailed numerical studies specifically looking at plume-lithosphere interaction leading to subduction initiation. And the ones that exist have pretty high uncertainty, like over 30% uncertainty in some key model parameters.
So the plume idea is plausible, but the detailed physics and evidence aren't fully nailed down yet for the early Earth.
That seems to be the situation, yeah. Lots of big fundamental questions still remain about the very origins of this critical Earth process.
Okay, so given these challenges and debates, where does the study suggest the field needs to go next? How can scientists fill these gaps?
It points towards pushing the envelope on several fronts. One is definitely continuing to improve that chronostratigraphy, the precise dating, aiming for even higher resolution, like 0.05 million years.
Even tighter timing.
Yeah, and combining that with analyzing the chemical zoning within single mineral grains, getting a time-resolved chemical history from individual crystals.
Incredible detail. What else?
Developing much more powerful geodynamic models. They talk about exascale models, computers capable of handling just immense calculations that can integrate really complex data sets like seismic anisotropy, how seismic waves travel differently in different directions deep underground,
Yeah.
and realistic mantle convection patterns.
You're building more sophisticated virtual Earths.
Basically, yeah. And a third key area is standardization, creating a unified global database for all known or suspected subduction initiation events using proper international data standards like ISO 19115, so everyone's comparing apples to apples.
Getting everyone on the same page with the data.
Exactly. The underlying message is that real progress requires intense interdisciplinary integration, bringing together the timing specialists, the rock chemists, the computer modelers, the deep seismic imagers, the field geologists.
All talking to each other.
Precisely. Integrating all those approaches is really the only way to build a truly unified theoretical framework for how subduction starts.
Wow. What a journey. We've gone from looking at publication charts and researcher networks all the way down to the specific minerals forming and the immense forces at play when a piece of Earth's crust first decides to take that plunge back into the mantle.
Yeah, it's quite something.
This deep dive, really guided by that systematic analysis of decades of work, gives you, the listener, such a structured way to grasp what scientists know, how they know it, and, importantly, what mysteries are still driving the research forward.
And understanding initial subduction really is fundamental. It connects to almost everything else about how our planet works. Mountain ranges, ocean basins, volcanoes, mineral resources. It's a field that's clearly advancing rapidly with all these new tools and integrated approaches.
Absolutely. And thinking about those big unanswered questions, especially the challenges in applying our modern understanding back to the early Earth, does that suggest, perhaps, that the rules of the game might have been fundamentally different on the young planet? Were the processes shaping Earth billions of years ago distinct from what we see today? And if they were, what does that really mean for our grand narrative of Earth's evolution?
That is definitely something to think about.